Hello friends, we will learn today Kani's method, and this is basically continuation of my previous video, and we are today going to solve problem 3. The distinct feature of problem 3 is that it has got one end fixed, that is A is fixed, and it has also got an overhang for 0.6 meters. So how to solve this problem using Kani's method, we'll see that. Okay, so we have got these 4 steps, very easy steps, and the first step is finding fixed end moments. So if you are not well versed with what are fixed end moments, I have just shown here few loading conditions for fixed end moments, and what you can do is you can pause the video if you want, and you can memorize them, or you can just write them. Basically you will require very few of these. This first condition is required, that is point load acting at the center of the beam, then point load acting at a distance A, and a UDL acting throughout the span. Only these 3 conditions are required, okay, to find the fixed end moment. So you can either memorize them, okay, and once you're done, we'll go and proceed with the problem. So first is to find fixed end moment at joint A, which is MFAB, and it is equal to minus WAB square by L square. You can use this formula, or you can also use the formulas minus WL by 8, since this load is acting at the center of the beam. But I prefer to use this formula, and it is minus WAB square by L square, where W is equal to 60, A is 2, B is 2, L is 4. I get it as minus 30. Why is it minus 30? Because since this load is acting vertically downwards, it will try to bend my beam like this in a sagging manner, and this will produce anti-clockwise resistive moment at A. Since the resistive moment is of anti-clockwise nature, according to my sign convention, I am considering anti-clockwise as negative. That is the reason I take it as negative, minus 30 kilonewton meter. Similarly, MFBA, here clockwise moment is acting, and I consider clockwise moment as positive. Thus it is positive WA square B by L square, and I again get it as 30 kilonewton meter. Fine. Now we'll find for MFBC. Again, fixed end moment at BC is minus WL square by 12, and it is equal to minus 53.3333, sign convention being the same as previous. And MFCB is WL square by 12, which is positive, and it is equal to plus 53.333 kilonewton meter. Okay. MFCD is equal to minus WAB square by L square, where W is 30, A is 2, B is 1, and L is 3. Alright, and it is equal to minus 6.6667 kilonewton meter. And MFDC is equal to WA square B by L square, where W is 30, A is 2, B is again 1, and L is 3, and it is equal to 13.333 kilonewton meter. The last fixed end moment MFDE, that is for overhang, is simple as we find it for a cantilever beam, and it is equal to minus W into L, again minus because this will try to bend my beam like this, and there will be an anti-clockwise resistive moment that will be produced for DE, and since anti-clockwise is negative, that is the reason we get it as minus 9 kilonewton meter. So we are done with the fixed end moments, and we are done with step 1. Now we'll go to step 2, that is rotation factors. If you have already done moment distribution method, this is very easy for you. We'll just write the joints, intermediate joints, whichever are there. So in our case, the intermediate joints are B and C only. D is not considered as intermediate joint. It will be considered as an end joint. Okay. So B and C are my intermediate joints. Connecting members are BA, BC to joint B, and CB and CD to joint C. Alright. And relative stiffness, this is my third column, and the relative stiffness is basically is the same thing that we have used into moment distribution method, but if you are not well versed with this concept, I'll just explain it to you in short how we get the formulas. This B is an intermediate support, it's an intermediate joint, and A and C are the end joints. Okay, for member BA, A is my far off support, that is A is the far off end, and if my far off end is fixed, my relative stiffness formula is EI by L, simply EI by L1. L1 is the length of the member BA, and for member BC, C is my far off end. Okay, and if my far off end is pin jointed, that is either it's a hinge or it's a roller, then my relative stiffness is basically 3 by 4 EI by L2, where L2 is the member length of BC. Only these two formulas you have to remember according to their end conditions, that is far off end conditions. Okay, so I guess you are now ready to go ahead. So we'll find the relative stiffness. For member BA, A is the far off end which is fixed, that is the reason relative stiffness is EI by L. For member BC, C is the far off end which is again considered to be as fixed because it's our primary assumption that all the intermediate supports are considered to be as fixed. Okay, and since B and C are intermediate supports, they are considered to be fixed as well. Thus it's EI by L. CB, since B is the far off end and it's considered to be as fixed, relative stiffness is EI by L. And CD, D is a roller support which is a pin jointed support, and therefore the relative stiffness is 3 by 4 EI by L. Got it? Now you have to just substitute everything I properly for every member. Okay, so it's EI by 4 since I is not changing for member BA. It's EI by 4 again for BC since I is not changing. For CB again EI by 4, and for CD it's 3 by 4 E into 2I, since for CD it is 2I by L. L is 3. Okay, now total relative stiffness is addition of relative stiffness of BA and BC. Okay, this is total relative stiffness for joint B, and total relative stiffness for joint C is addition of relative stiffness of joint of member CB and CD. Okay, so if I add these two, I get as EI by 2, and if I add these two, I get 3 by 4 EI. Alright, distribution factor is our next column, and it is equal to relative stiffness of member that is being considered divided by total relative stiffness. So it is equal to EI by 4 divided by EI by 2, which is equal to 0.5. Okay, for member BC again it is EI by 4 divided by EI by 2, which is 0.5. For member CB, EI by 4 divided by 3 by 4 EI, which is equal to 0.333. For CD it is 6 EI by 12. I've just simplified this. 6 EI by 12 divided by 3 by 4 EI, it is equal to 0.667. Okay, and the last column that we have to find is rotation factor. Rotation factor is equal to minus 0.5 of DF. DF meaning distribution factors. Okay, so rotation factor is equal to minus 0.25, minus 0.25, minus 0.1667, and minus 0.333. So we have found rotation factors, and step 2 is completed. Step 3, very important step, is drawing the Kani's box. Oops. Yeah, so step 3 is very important, drawing the Kani's box, and we have to draw these boxes. These are called as Kani's boxes. We have to draw them at intermediate supports. Since B and C are my intermediate supports, we have to draw them at intermediate supports, and outside the boxes we have to write the fixed end moments. So I'll just expand this tab, and fixed end moment for AB is minus 30, fixed end moment for BA is plus 30, fixed end moment for BC is minus 53.333, fixed end moment for CB is plus 53.333, fixed end moment for CD is minus 6.667. Don't worry, I'll explain you what I've done here. Okay, and fixed end moment for DC is plus 13.333. Okay, and the friction moment for D is minus 9. So basically what we have to do is, since this is a overhang and this beam is going to bend like this, okay, so the moment, whatever moment is produced here, it has to be balanced on both the sides. So if minus 9 kilonewton meter moment is produced on this side, so this side also has to have a moment of equal magnitude but of opposite nature, okay, so that this joint is balanced. That is called as balancing of joint basically. So we have to balance the moment here. If here it is minus 9, we have to do some procedure so that we get here as plus 9. The answer has to be plus 9. So currently we have a moment of plus 13.333. We'll do this 0 by adding a moment of minus 13.333. okay, and okay, now we have done this 0. Now we'll add a moment of plus 9, since the result that we want is plus 9. okay, so we'll add a moment of plus 9 and we'll sum it up. So final moment that we get here is plus 9. okay, and since we had added minus 13.333, we have to take it to the immediate support. okay, and it becomes half. I think I'll have to write this as half of this. It is equal to this divided by 2, minus 6.667. And again, since we added plus 9 as well, so we have to carry over it, and this becomes half here. So it is equal to 9 divided by 2, it is 4.5. okay, very easy. And we have to add them, we have to sum it up, and this is the final moment that we are going to use to write this value, to fill in the boxes in between. Now to fill in the boxes, we just have to sum it up, sum up the fixed end moments which are adjacent to the box. That is what I've done here is minus 53.333 plus 30, and that whatever answer you get, you have to write it in between at the center of the box. That is the summing up the moments. okay, again here the same thing we have to do, minus 8.833 plus 53.333. this is my summation of moments. okay, now we are ready for our iteration process. I recommend that you check my problem 1 as well, because in that problem I have explained Kani's box with a sort of animation, so for you to better understand. okay, so I recommend that you watch that video as well. Alright, so we'll start with our first iteration process. We'll write 0 and 0 here. At the ends we always will have to write 0 and 0. That is our first iteration values. Iteration value of BA will be equal to summation moment plus latest iteration value of C of left support, since A is to the left of B, and latest iteration value is 0, plus latest iteration value of right support, since C is to the right of B and there is no iteration value, so it will be taken as 0 itself, into the rotation factor of BA. okay, so this is the iteration value of BA. Now we'll find iteration value of BC by similar manner, that is summation of moment plus latest iteration value of left support plus latest iteration value of right support into rotation factor will give me the iteration value of BC. okay, again similar procedure, summation of moments plus latest iteration value of left support, since B is to the left of C and the latest iteration value is 5.833, plus latest iteration value of right support is 0, into the rotation factor. I get the iteration value of CB. This is equal to summation moments plus latest iteration value of left support, that is 5.833, plus latest iteration value of right support, okay, into the rotation factor of CD. Into the rotation factor of CD, I get my iteration value for CD. Okay, so this is our first iteration that is completed. We'll go for the next iteration. Again, we'll write 0 and 0 here. This is the first step that is to be followed before starting the iteration. Okay, the next thing that we'll do is, since I'm in Excel, I can copy it, but I'll show you the formula remains the same that we used previously. Okay, so this is summation moment plus latest iteration value of left support, which is 0, plus latest iteration value of right support. We have a value here which is equal to minus 8.3889 into the rotation factor for BA, thus we get iteration value of BA. Again the same thing here, summation moment plus latest iteration value of left support plus latest iteration value of right support, okay, and into the rotation factor, that is minus 0.25, we get the iteration value of BC. This is again summation moment 44.5 plus latest iteration value of left support. For B, the latest iteration value is 7.931, okay, plus latest iteration value of right support, which is 0, into rotation factor of CB, we get iteration value of CB. This is equal to summation moment plus latest iteration value of left support, that is 7.931, plus latest iteration value of right support, that is 0, into rotation factor of CD, we get iteration value of CD. Okay, this is our second iteration completed, the whole thing. Okay, we have to continue these iterations till we get these two values to be approximately equal. In our case they are exactly equal, as you can see here. Okay, so we have to continue these iterations till we get these two values approximately equal. Okay, and the final value that we get is what we are going to use for further calculations. Okay, so we have to do here 1 2 3 4 5 iterations to get exactly equal. It can be approximately equal as well, so it didn't matter if you stopped here, because even these values are approximately equal. Okay, so we'll use this value now enough to find the final moments. Our step 3 is done. All right, and we'll now find the final moments. So we'll first write the fixed end values here: MFAB minus 30, MFBA plus 30, MFBC minus 53.333, MFCB plus 53.333, MFCD is minus 8.833, and MFDC is plus 9. Okay, so actually we are not going to add anything to this value because we have already balanced it, so there is no need of balancing it further. Okay, so this we are not going to touch this support. All right, next is that you have to write the iteration values: 0, this value, here, and here. So next step is we have written all the iteration values. Now you just have to copy all these iteration values again and write them again. Okay, write them again. This is one step that you have to follow, and the next step is also very easy. You just have to cross paste them in cross directions. Okay, let me just get it correct. Alright, so what you have to do is you have to bring this value here Now just see that if this end was maybe a pin jointed end, since now it is fixed end. If this was a pin jointed end, you should not bring this value, because if it was a pin jointed end, you would have already balanced it here. Okay, like we have done it, like we have balanced this joint here, we would have also balanced it here, and then you would have to keep this joint as well untouched. Okay, then you don't have to carry anything on this joint. Everything that will be done would be on intermediate joints only. So basically now this is a fixed joint, we can carry it, and by carrying I mean you just have to paste these values here in cross manners. This value here, this value here, this value here, and now this value I will not take here because I have to leave this joint untouched. Okay, so I won't take it there. This is completed, and now we just have to add them up. It is equal to summation of all the moments that's it. So these are my final moments, as you can see here. These are all my final moments, and these values have to match exactly and have to be opposite in nature. By opposite in nature I mean that if this is plus, this has to be negative. Again, these are matching. Okay, and here it is +9. So we have now successfully analyzed this problem as well. Okay, and that's it for today.